Hello, and thank you for checking out this presentation in our paper, where we introduce a unified approach for managing heterogeneous processing elements on FPGAs. We look to address the fact that FPGAs contain a large number of different processing elements. So in addition to the traditional lookup tables, DSPs, and memory blocks, there's also embedded processing elements like CPU cores or new application or domain-specific processors. And so the problem lies in bringing all these different processing elements together. Their different implementations, pipeline lengths, latencies, behaviors, etc. And so therefore the goal of our work is to bring all these processing elements together and create a unified approach for managing these different processing elements and ultimately make it easier to create designs that use all of the FPGA's processing elements. Our central idea is to group together different FPGA processing elements into unified compute pools. Processing elements are grouped according to their function, not their resource composition. So, for example, you might have a compute pool that performs the square root function, and this would contain a number of heterogeneous processing elements, and each one would perform the square root function, but it might perform it in different ways with different implementations, different latencies, and each processing element might use different resources. But with our compute pools, all of these elements are unified by their function. Different implementations, but the same function. And so our compute pools bring these different processing elements together. And so a pool would be composed of E processing elements and able to serve D parallel function calls to its implemented function. These centralized compute pools are logically, not physically centralized, and uses a scalable interconnect to manage and arbitrate access to the E processing elements inside the compute pool. And so we can add or remove processing elements to meet the needs of the applications or the limitations of the target FPGA device. We can use more resources when available or use fewer resources to make the application more compatible with smaller FPGAs. Our compute pools bring together different heterogeneous processing elements, so we must support all of these different implementations and connections. And we do this with a call and response approach to computation. So each processing element has a call unit, which is essentially the input to the processing element, and in addition to this, a response unit, which will return the result of a given function call after L cycles. Our interconnect and performance model deal with processing elements based solely on this latency. So it doesn't matter about the exact processing element implementation or its behavior. All we're concerned about is the end-to-end latency. And so with this method, we can unify all of these different heterogeneous processing elements into a single unified compute pool. When evaluating our compute pool approach, we first compare just the framework itself without any processing elements. So for 32-bit data path designs, we can see that our framework scales linearly with parallelism. That is the number of parallel data paths or number of parallel function calls. So when moving from 16 parallel data paths to 1024, which is a 64 times increase in parallelism, we need just 23.8 times the resources. Resource utilization is another issue. So for more homogeneous, coarse-grained architectures, they tend to see issues with poor resource utilization. So these past approaches tend to define entirely new processing elements rather than bring together existing processing elements like our compute pools do. And so the problem with these past approaches is that if an application's resource use doesn't exactly match the resources of these new processing elements, then the resources are wasted. These resources are locked away inside the newly defined processing elements. So our compute pools don't face this issue. We bring together existing processing elements rather than define our own, and so are therefore able to achieve very high resource utilizations. So this is 96.2% for 1024 parallel paths, and can actually rise to 99.8% if using 16 parallel data paths. When comparing directly to these more coarse-grained architectures, we see a 10 to 24 times improvement in throughput. We see improvements both in the raw throughput and the per resource performance. With our 32-bit floating point implementations, we're actually able to outperform even the simpler 16-bit integer frameworks. Another important point is that by uniting processing elements by their function, we don't need any new development tools or tool chains. This means that as well as supporting all existing processing elements, we also support all the different tools and tool chains and processes that were used to create them. So application developers can then make use of our new compute pools using their existing development flows. We now look at the performance of applications designed with our new compute pools. For this, we implement a range of different neural network activation functions. And these test functions range in complexity from very simple to large multi-cycle functions. And we look to serve 1024 parallel function calls using different numbers of processing elements. So 8 processing elements to serve all 1024 calls, or 16 processing elements to serve 1024 calls all the way up to 1024 elements. So adding and removing processing elements is very simple with our compute pools. Without modifying the actual design, you can easily add or remove processing elements to get the design to fit into the resource and performance budget of your target FPGA. So adding or removing processing elements naturally affects performance. But we demonstrate that the peak performance, the maximum throughput or the minimum latency, occurs before we reach the maximum number of available processing elements. We see the best performance tends to occur when between 64 and 256 processing elements serve the 1024 parallel function calls. This is due to less congested designs that result in higher operating frequencies, for which we see an average improvement of 21% for throughput and 29% for latency when compared to designs that maximize the number of available processing elements. So, in summary, with our work, we look to make use of all of the processing elements within FPGAs through the use of our new compute pool architecture. Our compute pools group processing elements by their function, not their resource composition. And so, through our call and response approach to computation, we support different processing element implementations, latencies, pipeline lengths, and complexities. With our new high-level framework, we don't define new processing elements, but instead collect together existing processing elements. And so therefore we don't need whole new development tools and tool chains, and are then compatible with all existing FPGA application development flows. When evaluating our framework, we demonstrate a 10 to 24 times improvement in throughput, and also a 96.2% resource utilization. And this is higher than past works, which typically see issues with FPGA resources being locked away in their newly defined frameworks. Looking at applications designed with our new compute pools, we see that the best throughput and latencies occur before we reach the maximum number of processing elements that are available on the FPGA. And in general, we find that supporting and managing access to FPGA processing elements is the key to creating higher performing designs, not simply a matter of maximizing resource use. Thank you for your time, and please get in touch if you have any questions or suggestions.